Let's return to our example, just so we can really nail down on some of these definitions, make sure we know what we're talking about with our language. So again, we're looking at traffic congestion levels across these four continents. We have 10 cities in each continent. So let's first think about our factor variable. So our factor here. So we have, what, 4 levels of continent, right? So we're going to say our factor here is continent with C equal to 4 levels. 4 levels because we have 4 continents, right? 1, 2, 3, 4. Our response variable. So this is congestion level defined as the increase in overall travel time when compared to a free flow situation. So I'll abbreviate that. We'll just say increase in travel time due to traffic congestion. Okay, our assumptions. Well, first, that is normality. So we could create box plots for, or rather histograms, and see if the histograms look normally distributed. Our problem is that we only have 10 cities for each of these, so there's only 10 observations here, 10 here, 10 here, 10 here. So that's not going to be super helpful. So this is going to be something that's challenging to test anyway with such a small sample. But if we look, we can kind of see that these are all fairly symmetric, right? Like for example, where the median is, this distance is not super far from this distance. Um, I don't know, the means aren't super far away from the median. So here we're kind of have to just take it for what it is. We're going to say yes, box plots look symmetric. Our sample size n too small for box plots. Okay, 2, equal variance. So there's a number of ways we could check. So that's one, comparing the interquartile ranges. So they're obviously different from one another, but I mean, this one is the most different, but I don't know. Nothing is vastly different from one another. We can also look at the overall range. Again, there's obviously differences, but are any of them so dramatic to suggest that you don't have equal variance? So we'll say no, or we'll say yes, we have equal variances. We'll just say variances are fairly similar. Of course, for this class, when we do examples, we kind of need these assumptions to hold true. But it is important that we keep track of what our assumptions are as we work through these problems. So we definitely need to know what our assumptions are. So independent, and that's true, yes. We could say traffic in one continent doesn't affect traffic in another continent. Again, we don't have the ability to assign cities to a continent, so we didn't really design this experiment or assign cities to a continent, so we don't really have the benefit of random sampling, but in one sense that these are still independent just because one isn't going to affect the other. These are independent populations. Their distributions are independent from one another. Okay, our hypotheses, so let's just write those out. Our null would be that all the means are equal to each other. So I'll just say mu sub Asia would be equal to mu sub Europe, oops, equal to mu sub North America is equal to mu sub South America. Then our alternative is simply that H naught is false. So the question that research question we're trying to answer here is whether is traffic congestion different across continents? And that's really what we're doing with ANOVA. So is our response variable, so is our response different across our factor? So is our response variable, traffic congestion, different across different levels of our factor or continents? That is ultimately what we are looking at with ANOVA. We've got 3 or more levels of a factor. Is our response variable different between those different levels of the factor? Is traffic congestion different across the continents?